Yeah, sometimes screen, sometimes both. Yes, yes. Okay. Thank you. Okay. So, good morning, everyone. Welcome to today's session. Yesterday, we discussed elaborately about Reynolds averaging, how to average the Navier-Stokes equation that gives us the turbulent flow field quickly without resolving much of the eddies or going intensive computation. So, at the end of averaging, we find but the problem becomes open. The number of unknown is more than the number of equation. We need some kind of approximation to close the problem, right? Unless we make some approximation, some additional approximation to for some unknown variables that appear out because of the averaging, the problems are open. We cannot solve it. And the art of approximating those unknown variable is known as RANS modeling, right? So yesterday we discussed about the most simple approximation that almost done 70-80 years back, around almost 100 years back by modern father of modern fluid mechanics, Ludwig Prandtl, that has done almost 100 years back in 1925. That is the mixing length model, right? He approximated analogous to the kinetic theory of gases, where the mean free path is responsible for the mixing between the or Brownian motion between the gas particle. Analogous to, he approximated a mixing length for eddies. Okay, mean free path is the distance traveled by the molecule between two successive collision, whereas the for eddies the mixing length is the distance traveled, the distance between the eddies between two successive time over, right? So he assumed the mixing length, but again after the approximation of the mixing length also, so the mixing length is not just a known quantity, right? You have to do a lot of analytical derivation and calculation. Then for a particular problem, you are getting mixing length in terms of its characteristics length. Just like there are few simplified model, right? Just like flow across the cylinder, where the wake region you are getting mixing length in terms of the width of the wake, right? Or the boundary layer flow, or the jet spreading, or the mixing of the two shearing layer. For them, you are getting some empirical data for the mixing length. But this empirical data of mixing length are only applicable to those problems. Even if you change little bit the problem, instead of the circular cylinder, if you put a square cylinder and measure the length, the mixing length model is not going to work, right? Then what to do? The turbulence is generic in nature, right? It is everywhere. You cannot enforce, okay, if this is the geometry, this mixing length is working. So we have infinite number of geometry, we are infinite number of situation. We cannot have always find mixing length for every problem, right? Then subsequently what happened? Okay, so we cover the laws of wall. Yeah, so come over here. So that was the limitation of the Prandtl's mixing length model, right? There are subsequently many attempts, okay, to address those shortcomings, whether there is any way that we can more precisely determine the turbulence eddy viscosity, okay, without doing all such particular problem finding a particular mixing length, right? So around the same Prandtl, around 1945, instead of solving an algebraic equation, he solved additional one differential equation for turbulent kinetic energy, right? That is called one equation model, right? For mixing length, he was not solving any additional equation. It's a zero equation model. So out of some algebraic expression, he was finding the mixing length for a particular problem. It was in 1925. After the 20 year, it was Prandtl who solved first the turbulent kinetic energy, additional differential equation. It's a again convection diffusion equation pattern. He solved it to find the expression for turbulent kinetic energy in terms of the different solution of the differential equation, right? It was called one equation model. Again, it was again shortcoming. With one equation, there are a lot of unknown that cannot be found. Okay, so then subsequently there are much more attempt. Okay, can we solve some additional equations or some additional methods should we consider to make the problem close? Then successively it came to the Kolmogorov, right, in 1942, who introduced the specific dissipation rate omega, right? Last time we discussed yesterday what is dissipation, right? Epsilon. Dissipation per kinetic energy. It's clear what is kinetic energy? The kinetic energy of the fluctuation in a turbulent flow field is the turbulent kinetic energy. Dissipation means it's the at the smallest scale the amount of energy liberated from the system is the dissipation, right? Dissipation per unit kinetic energy is the specific dissipation, right? He was a statistician. He was not much a fluid dynamics or not a computational specific, but he was an excellent mathematician and statistician, the Kolmogorov, right? What he did from the dimensional analysis is found how this eddy viscosity or the turbulent viscosity that is related to the kinetic energy and dissipation. He found the dimension of the eddy viscosity is same as that of the dimension of the ratio of the kinetic energy to the specific dissipation, right? Then if this is the eddy viscosity dimension, then he found the mixing length dimension for a problem, it's order of square root of the kinetic energy by dissipation. If you are finding only dissipation, this is omega is the specific dissipation. Dissipation per unit kinetic energy. Then what is the total dissipation? Total dissipation is equal to omega times k. Okay. So this is how people started solving a two equation model. The idea is to find one length scale associated with the eddy, one time scale. What physicality is telling? This gives pictorially the representation, the length. Okay, if suppose this is the eddy, this gives the length of the eddy, right? Then this gives the time scale. Means once you know the length, once you know the time scale, you get the velocity, right? Then additionally, the theoretical idea is to find the associated length and the time scale with the eddy so that we can find the eddy turnover time. Clear? So from the subsequently in 1945, okay, there are people started using these two things to compute length scale and time scale. They started solving two convection diffusion or two differential equation, right? After solving two differential equation, they find some length scale associated with eddies, some time scale associated with eddies, and from the ratio of the kinetic energy square to epsilon, they found this is giving the eddy viscosity, which was the unknown for the closure problem. Now it is clear. It is Rota around 1951, right? He developed the new two equation model. That is the modern form of what we call K epsilon model, right? It was developed around 1950 after the Second World War. There is a lot of research. They based on Imperial College London, Germany. So basically that time after the post World War, so they were developing some chimneys in the European architecture or the home. They are developing some chimney for proper scavenging of the exhaust gas for the chimney. So they are developing, if it is turbulent, they will be rapidly exhaust. So for that, the government sanctioned a lot of money project. So there are groups in Imperial College London, Calsue, somewhere in France. They extensively work on all those models. They came out of their dedicated research for next 30-40 years of time, right? So now coming to the simplest two equation model. So in 1951, So Rota involved in the solution of two turbulent scale. In 1945, Prandtl solved one equation for turbulence kinetic energy, right? Instead of solving one equation, 1951 Rota started solving two equations to simultaneously determine two scales. One is length scale or one is time scale associated with the eddies, and successfully closed the equation based on the Kolmogorov hypothesis that Kolmogorov formulated in 1940s, right? So the most simplified form of two equation RANS is the standard K epsilon equation. It was developed by Brian Londo. Okay. Then Jones and Londo, they again works on Imperial College. I think Brian Londo is still active. Professor Brian Londo, he is in Manchester, right? With Kamal Hengelik, with other people. He worked extensively on the RANS. So in 1970s, okay, they came up with the most simple version of the two equation model that is still yet in practice for most of the engineering flow. That is called standard K epsilon model, right? Last time we have solved the equation for turbulent kinetic energy. Have you seen the form? Have you seen the form of the equation for turbulent kinetic energy? You remember, right? So what this side is representing? Here is my turbulent kinetic energy. What this side is representing is the convective acceleration. This is a time variation of the turbulent kinetic energy. This is the convective acceleration of the turbulent kinetic energy. Then again, instead of this is the molecular or viscous diffusion of the turbulent kinetic energy, there are additional second order and third order correlation term which cannot be determined independently because the problem was open. Yeah, you can see, okay, once we derive the exact equation for turbulent kinetic energy, you can find there are additional third order correlation, pressure velocity fluctuation correlation. These are open, these are not known. Somewhere we have to make approximation to close this, right? To close it, then in 1974, Professor Brian Londo and Jones, okay, they developed the standard K epsilon model. They assume it, okay, those sort of third order correlation and pressure strain correlation in terms of equivalent diffusion, that is diffused by the turbulent field. Okay, this is apart from the molecular diffusion, there are some enhanced diffusion, right? Then they scale those enhanced diffusion proportional to the eddy viscosity times some proportionality constant. All right, so now there is apart from the molecular diffusion some additional diffusion is there because of the turbulent flow field, and they put it the eddy viscosity times some sigma k. This is some coefficient which is a constant coefficient or calibrated based upon the experiment. They found it. So all those third order correlation, pressure strain correlation, they dumps into the equivalent diffusion term, right? Once this diffusion term is there, this is the dissipation term, the amount of energy that is destructed or going away from the system. There comes appear in terms of epsilon, right? It was already yesterday we have derived. Then there are production term. Production means the mechanism by which the turbulent is extracting energy from the mean flow. So they based upon the situation, the flow situation, the production will be different. If it is a shear driven flow, the energy will be extracted because of the mean shear. Suppose it's a quiet flow, it's a Plausily flow, there is a shear difference between the layer, right? The amount of energy will be extracted because of the mean shear in the flow field. But if it is a natural convection, suppose Rayleigh-Bénard convection, buoyancy driven convection, apart from the shear, because of the buoyancy force, right, there will be some production of energy production, turbulent kinetic energy production. So in generic sense, the turbulent energy production of two types. One we have defined, one is the production due to shear, one is production due to buoyancy. Now it is clear. So now from last 2 years I was working on the bubble driven turbulence. Okay, the turbulence is generated because of the generation of the micro bubbles at the fluid. In that case we have a apart from these two, we have another kind of production mechanism that is called bubble driven turbulence. The production is because of the bubble nucleation, right? Similarly, if you have different source for generating the turbulence, you have a different mechanism for the production. Currently, we have the production because of the turbulent kinetic energy, extracting energy from the because of the mean shear. This is because of the buoyancy. Things are clear. So once you at this stage, this equation is closed, right? We can solve this differential equation if nu is known, nu to t is the only unknown we have to determine, right? Then this term we can, these are the average quantity we can calculate, right? Then we need to solve additional equation for epsilon, right? Then the additional equation for epsilon looks pretty. This is the thing. We did the derivation for the diffusion term that we have already covered. This is how the production due to the shear looks like. This is the mean strain rate. Clear? This is the term that the production due to shear, right? So this once you get, then we have an additional equation for the dissipation, right? Again, it's the same similar equation. Okay, advection diffusion equation. So what are the things? So this is the convective part of the dissipation. It is time variation. One is giving convective acceleration in the flow field, right? This is again the third order correlation, etc. that dumped into a equivalent diffusivity into the turbulent flow field that was captured at the scale sigma epsilon. This is some different coefficient, right? So they are scales with the eddy viscosity, right? Divided by sigma epsilon. Then this is giving the equivalent diffusion, that is laminar diffusion or viscous diffusion plus turbulent diffusion, right? Then because of the buoyancy production, okay, there is some production term also in the epsilon equation, right? Then there is some destruction term. At every time step, some amount of energy is continuously liberating from the system. There is some epsilon that is going away from the system, dissipation. It's clear? So as I made, Kamal Hanzelik, Harlow Nakama, there are a lot of other people in 1970s, those who were working in the Imperial College, London, they developed all sorts of models subsequently, different variant of the K epsilon model. So this is the standard K epsilon model. Okay. Once you solve these two equations, one for turbulent kinetic energy, one for the dissipation, you will get K and epsilon. Now, what next? What is the unknown we have to determine? What is the unknown in these two equations and Navier-Stokes equation? Eddy viscosity nu t, we don't know, right? Then once the K and epsilon is known, these are the correlation that we approximated in terms of the known quantity. So once we solve the K and epsilon, then the eddy viscosity they propose, it is some proportionality constant C mu times K square epsilon. You understand what is the logic between solving two equations? You solve additional partial differential equation for K, you will get the value of K. You solve partial differential for epsilon, you get the value of epsilon. Then you calculate in the flow field at every point, you calculate the eddy viscosity equal to C mu into K square by epsilon. This terms C mu epsilon 2 epsilon 6 sigma times K, all those things are empirical coefficient. They are not defined mathematically derived somewhere other than from the data fitting or from the experimental correlation they are defined. Okay, let's see. For a standard K epsilon model, there are different variants, right? Over 3-4 years of time, Jones and Lunder in 1972, they first gives the model, they prescribe some value, then subsequently Lunder and Spalding, okay, the same brand Spalding, the author of the book Patankar and Spalding, right? He also did the thing, they find it, then Lunder and Sharma, they also did the experiment, they found some value. Like this, the standard K epsilon model was developed, right? Then this closure coefficient was determined from the empirical relation that fits with the experiment. Okay, someone did experiment more precisely, fine tune the data, then they find some accurate coefficient subsequently over 2-3 years of time. It's clear what is standard Epsilon model or any doubt? Clear? It is clear what is standard Epsilon model? Now you can answer what is standard Epsilon model. There is no doubt, absolutely. Okay. It was initially developed. This was standardized against the experimental data. Then it was called standard Epsilon model. We are solving additionally two equations. One for k to give the velocity scale. Square root of k will give the velocity scale. Epsilon give you the time scale. Subsequently, you can from the velocity and time you can calculate the length and time, or length and time you can calculate the velocity. Right? Clear? Then what happened? This was just one model. People across the globe started simultaneously developing model that fits the experimental data in much precise manner. Right? There are some other mathematicians, statisticians, they came with some new model. Okay, this is let's see. This is for a channel flow. Okay, this is for a channel flow. These are the dotted is the what you call experimental data. The black solid line is the data that obtained from the Epsilon equation. You can see how closely they are matching for a channel flow. This is a backward facing step. This is the experimental data for the velocity, and this is my Epsilon model data. This is a flow in a bent U-bent pipe. You can find how closely they are matching. Okay. After this is a boundary layer profile. You can find there is some deviation between the CFD data from the Epsilon model and the experiment in the boundary layer. All other three conditions they match successfully. Then subsequently people started improving those models based upon some statistical theory, some other parameter, right? Then subsequently realizable Epsilon model was developed. What is the condition for realizability? Okay, the condition for realizability telling your Reynolds stress should be positive and definite, right? So this is the your Reynolds stress is the matrix, right? 3 cross 3 matrix, or it's a tensor, right? It has some property, right? The some statistical property should be preserved. What is that? The diagonal term, okay, the square of the diagonal term, average term, should be greater than 0. Means if you write the Reynolds stress, why? Because turbulence kinetic energy is always positive. So right now, if I write tau 11, tau 12, tau 13, tau 21, tau 22, tau 23, tau 31, tau 32. It is telling this diagonal term, right, should be greater than equal to 0. The kinetic energy should be positive. The square of any quantity should be positive or not. Clear? Then the average of the ui uj, okay, if you square the average quantity, that should be less than equal to average of the square quantity. Okay, this is additional requirement for realizability, right? First you do the Reynolds averaging of the Reynolds stress, okay, then you take the square. That quantity should be less than, first you square the fluctuation quantity and make the averaging, right? This is additional requirement for realizability. Okay, the third realizability condition is mentioned over here. Okay, it's a quite lengthy distribution. It comes from the meticulous derivation by the statistician. Okay, if this three condition is satisfied, then it is called Reynolds stress is realizable, right? To satisfy these three conditions, okay, so they developed additional C et al. In 1995, again after 30 years of time, 75 to 95, 20 years of time, they developed additional equation called realizable K omega. In this realizable K omega and standard K omega, the K equation remain unchanged. There is not any change in the governing equation for K. The K equation looks as it is. So what happened? What is the difference? Then the difference is that the epsilon equation, right? They are looking different for the standard K epsilon to realizable K epsilon, right? So for the realizable K epsilon, there are some new term appear. This is the, what do you call, thermal buoyancy, 3p times. Okay. The mean shear, this term appear in terms of the mean shear rate, right? There are some additional deviation in the epsilon equation. If you compare it, C epsilon 2 epsilon square by K, right? C1 epsilon by K. Okay, if you compare this term to equation, you will find K plus root over of kinematic viscosity times epsilon root over. This term is coming additionally inside the denominator, right? So this kind of modification that comes from the that satisfy the realizability condition for a matrix. That's why they called it realizable K epsilon model. Clear? The difference between standard K epsilon model and realizable K epsilon model in the for both cases, kinetic energy, the form of the kinetic energy remains same. Only the equation for the dissipation they change. Now it is clear what standard K epsilon model, what is realizable K epsilon model, right? Then subsequently, people renormalize the group again. Okay, for realizable K epsilon model, the closure coefficients for standard K epsilon model, this C mu, the way the eddy viscosity is calculated, they remain same. But earlier, for standard K epsilon model, this C mu is a constant, 0.09, this is value. But when it comes to the realizable K epsilon, they are no more constant. They are depend upon additional some parameter. Okay, this is omega, is the mean vorticity, right? These are epsilon ijk, they call the Levi-Civita tensor. Okay, this is a permutation variable in the third order tensor. Okay, so based upon this value, the C mu is calculated. For the whole flow field, C mu is constant for standard K epsilon, but for realizable K epsilon, this C mu coefficient that scales K square to epsilon, they vary in the flow field, right? So this is how the realizable K epsilon is very different from the standard K epsilon model. Earlier we have a C mu over here, but here C mu is a constant 0.09. Now from the realizability condition, we get a C mu in terms of some algebraic equation. For that algebraic equation, we have to solve the mean strain rate, mean vorticity of the flow field, then only we'll get it. So that it is a field variable right now, C mu. Throughout the flow field, it changes its magnitude based upon the point. Clear? Then subsequently, okay, these are all how you define the mean strain rate and all. This is given. Okay. Now see the deficiency or the shortcoming of the standard K epsilon model and how the realizable K epsilon model works well. So this is the experimental data. Okay, the standard K epsilon model was giving some deviation from the experimental data. When they renormalize realizable K epsilon model, they work some relatively good fit, right? This is also for some planar jet. They also matches both standard K epsilon and realizable. They produce the ideal result, identical result. This is for a bent tube where the standard K epsilon model was failing completely. The realizable one close to the experimental data, right? The same with the rounded jet, spreading of a rounded jet, right? So within 20 years of time, there was an attempt subsequently to improve the Epsilon model developed by the London in 1975. So by 1995, this realizable Epsilon model that came into picture. Clear? Then subsequently, what happened? People started doing the research. They developed RNG Epsilon, which is called renormalization, right? Basically, renormalization is a concept in the Lie group or a mathematical concept. Okay, it's mostly understood by mathematicians or statisticians, not much by the engineers, unless they are very deep into mathematics. So, okay, they Yakot et al. In 1992, they renormalize those field variable or the statistical variable, right? So they renormalize this group, and that's why I call RNG, renormalized Epsilon model. They develop another Epsilon model. But the good thing is that all these three Epsilon model, the governing equation for the K, they look similar. What was the only change? Epsilon. So now see how epsilon looks in the RNG epsilon model. So here we have convective term, here we have a diffusion term, here we have a production term due to buoyancy, production term due to shear, mean shear. Then the coefficient, what coefficient earlier there in the standard epsilon model, they are constant. They are no more constant in the RNG epsilon model. They are function of some other parameter which are determined from the mean strain rate or mean vorticity. Yeah. So once whether it is standard epsilon, whether it is RNG epsilon, whether it is realizable epsilon, once you calculate K and epsilon, the formula for calculating eddy viscosity remain unchanged. So in the realizable epsilon, the C mu was also a variable, right? Once again you come to RNG epsilon, C mu become the constant. It is 0.09 for the standard epsilon. For realizable, it is a variable. For RNG, it is around 0.0845. But the form remains same. The coefficient, the form remains same. The coefficient somewhere behaves as a constant of value 0.09, somewhere 0.0845, and somewhere it depends upon the field variable, like mean strain rate or mean vorticity. Now it is clear. This is clear. What is K epsilon model? Or any doubt? Now it is clear. K epsilon model. So everyone is using K epsilon model in the console or ANSYS or OpenFOAM, anywhere you are using ANSYS Fluent. You see the K epsilon model, right? Now it is clear what is K, what is epsilon, and what is K epsilon model, or any doubt is there? I don't know. If I know, then the rest all would know which problem, which model. That's again a heuristic approach. Then may one model may good for particular problem. The one model may be fail for particular problem. So because these are not something physical, based on the empirical relation, the coefficient, closure coefficients are evaluated. So they may give the good result, they may fail. That's why there are oceans of RANS model available. See, if you are asking me which one is giving good result, let's see. The dotted line is the experiment, right? This is the solid line is the standard epsilon model. You can see the standard epsilon model gives a much deviation from the experimental result, right? Then there is a realizable epsilon and there is RNG epsilon. Okay. So the realizable epsilon was this line is the realizable, right? Right. The realizable epsilon gives slightly better match this side. Okay. This side that gives the slightly better match. The RNG epsilon that gives the better match of this side, while they also underestimate the flow velocity at this side. Okay, the RNG gives the good valuation, right? Hmm? They have some nozzle, Knox diffusion, yeah, diffusion nozzle. This is a diffusion. They are measuring the velocity. So it is very difficult to say which model is universal applicable. None of this model is universal applicable. These are problem specific. So one model may produce good result for a channel flow, for a backward facing step, but it fails for other kind of geometry. The problem with RANS that the closure coefficients, they are dependent upon the geometry or the problem specific. Clear? So now you know that in this additional two equation model, you have to solve two equations, K and epsilon. Then after solving those two equations, you will find the eddy viscosity, right? Once eddy viscosity is known, then you can solve the Navier-Stokes equation putting eddy viscosity in its viscous term, which is adding it with the viscous term, so that it gives the effective viscosity. Now the models are closed, but still many things are remain unanswered, right? When you solve the additional two partial differential equation, you need boundary condition or not? You need boundary condition. Boundary condition for what? We are solving the equation for K and we are solving the equation for epsilon. You need boundary condition for both K and both epsilon, right? Those we will discuss, okay? So in the subsequent lecture, we will discuss the boundary condition for K and epsilon. Should we stop the lecture and have a small 5 minutes break? If it is heavy dose of session, then we'll take another 10 minutes break. Again, we'll shortly come back. Clear? Okay. Thank you, everyone. Let's come back soon after a short break.